Travel has always been a fact of business life. Today, it's executives flying business class for meetings all over the country. Not so many years ago, however, business travel brought to most people's minds an archetype of American folklore, the traveling salesman. Now, traveling for business, whether you're going to make a sale or hold a meeting, has to be efficient. You want to spend as much time as you can working and as little time as necessary getting there. So traveling salesmen of old and executive secretaries today try to plan routes that hit the required stops with the lowest total mileage.
Aboard!
Now we're on the right track. Of course, you could work out the problem of planning the most efficient route with a highway map or an airline schedule. It just wouldn't be as much fun. Suppose you're based in Chicago here, and you have to visit St. Louis, Cleveland, and Minneapolis on business. The train is making a circuit. It starts in Chicago, travels through Minneapolis, St. Louis, Cleveland, and returns where it started without going through any city twice. Now, to be efficient with your time and economical with your train fares, the problem is to figure out what route, the one the train is following or some other, is the shortest possible trip through all these towns. At first glance, this doesn't seem like much of a problem. After all, it's easy enough to find out the mileage between each pair of cities. Then you could write down every possible trip with the mileage for each leg and calculate the length of each trip. The most efficient trip is the one with the shortest total length. I could do this with the train, but since the same approach works for cars or airplanes, let's use a diagram instead. Since we're starting in Chicago, we have three choices of where to go first. If you pick Minneapolis, you only have two choices for the next stop, Cleveland or St. Louis. No matter which you choose, the next stop will have to be the other, and the trip will end with a return to Chicago. Now hop back up to the first place you made a choice. If you pick St. Louis instead, you could work out another branch of this tree diagram. And of course, the same applies if you go to Cleveland first. Well, that seems to be all the possible trips, 6 of them. But compare the first one and the last one, and you'll see that the cities are in the same order, just reversed. What seems to be 6 different trips are really only 3 distinct ones. This one is clearly the shortest. So the technique is just about as straightforward as it appeared. But what if we're planning a more ambitious trip, with more stops? There's a formula that will always tell us how many possible trips there are. If n is the total number of cities, then the number of choices for the first stop is n-1. The number of choices for the second stop is n-2, and so on down to 1. To find the number of different routes, we multiply out, and as we saw, divide by 2, since half of the trips are counted as repeats. In our example, n, the number of cities, was 4. So the answer is 3 times 2 times 1, or 6, divided by 2, which gives us our 3 different routes. The formula tells us how many trips there are. Actually laying out each one on a tree and adding up the mileages is the procedure we specified for determining the most efficient trip. Such a step-by-step procedure is what mathematicians call an algorithm. So we can now proudly say that we have an algorithm, a conceptually easy one at that, for finding the most efficient tour. There's just one hitch. We run smack into something else mathematicians have a name for, the combinatorial explosion. It sounds bad, and it is. Suppose we try to apply our simple algorithm to a trip visiting 11 cities. With n equal to 11, it turns out there are approximately 20 million possible tours. That means adding up the mileages for 20 million different routes in order to find the shortest tour. No problem, you say. Let the computer do it. Fair enough, but consider this. If we want to visit 25 cities, that's a long sales trip, but business is tough. And if the computer can generate 1 million tours every second, it would still take 10 billion years to list all the possible tours. That may be enough to convince our salesman to visit fewer cities. What we actually want, of course, is not to visit fewer cities, but a better solution method. And mathematicians have been studying alternative methods for this kind of problem for a long time. For historical reasons, this problem is called the traveling salesman problem. But the very same idea comes up in many different situations. Utility companies face it, for example. Just imagine that instead of cities, the stops are phone booths or electric meters. In both cases, someone has to start at a home base, visit a number of sites to collect the coins or read the meters, and return to base. The numbers we use could still be distances, but they might also represent times or transportation cost. There are even examples that don't seem like travel at all. In order to build this circuit board, engineers have to insert integrated circuit chips at a number of locations. That means moving the inserter around the board, a very different kind of tour, but nevertheless a route that the manufacturer wants to make as efficient as possible. Traveling around a city block collecting garbage from specific sites is much like traveling around a circuit board. The men on the truck have to follow a certain route, beginning at one end of town, picking up the trash as they go along, and ending up back where they started. Of course, that isn't the most exciting round trip we could make, considering that the same techniques used to solve the traveling salesman problem can easily be applied to routing airplanes all around the world. Some of these examples may have hundreds of places to visit, but as we've seen, the computation required by our algorithm becomes impossibly enormous with just 25 places. So we need to think about a more manageable method of solving this problem. Let's go back to a simple case, the four-city trip. Now, a natural way to find our route might be to decide to go to the closest possible city. Starting at Chicago, the closest possible place is St. Louis, only 300 miles away. From there, the closest place is Cleveland. Now, from Cleveland, the closest place is Chicago, but remember that our goal is the shortest trip that visits each city just once. So from Cleveland, we're forced to make this relatively long link to Minneapolis and then back to Chicago. This way of figuring out a tour follows a specified procedure, so it too is an algorithm. If you're starting to feel that mathematics has overly fancy names for everything, though, you'll be glad to know that the name of this procedure is the nearest neighbor algorithm. This method is pretty simple to follow. It's easy to see that a computer, or even a mere person, could figure out a nearest neighbor solution to even a large traveling salesman problem quite rapidly. So there must be something wrong with it, right? And there is. Notice that the trip we planned with the nearest neighbor method is not the shortest possible one. In other words, we have a trade-off. The algorithm generates a solution quickly, but that solution isn't the best one we could have found. Well, whether you're a sales manager or a mathematician, you'd like to have the optimal solution. As we've seen before, this is the real goal of management science problem solving, finding the best answer, where best may mean cheapest, most efficient, or in this case, shortest. So are there any other approaches? Let's see what happens if we arrange all the distances from smallest to largest. With the links listed in decreasing order, we can create a tour by putting in the shortest links first. You can think of this as a greedy method where we put in the cheapest elements and try to minimize the cost of the tour. Chicago to St. Louis is still the first step. The next is Chicago to Cleveland. But since we're now adding the links strictly by this greedy factor, rather than moving to the nearest neighboring city as we did before, the greedy approach may not look like it's producing a solution until the entire tour is formed. So the next step would be Chicago to Minneapolis, but we don't allow that one. Why not? Remember that we're not allowed to visit each city more than once. On a diagram like this, that translates into saying that there can't be more than two lines running into any one point. In the language of graphs, we'd say that there can't be more than two edges meeting at any one vertex. If we did allow that, we'd have to revisit some city. The next cheapest link is Cleveland-St. Louis, but that would create a subcircuit, so it's out. That leaves two last links that we fill in. Guess what? The tour we've traced, even though it's generated by putting in the cheapest legal links at each stage, is again not the most efficient overall tour. In fact, the very original one we constructed turns out to be the optimal tour for this particular collection of cities. Evidently, we're in a bit of a rut. We have one algorithm, what we might call the brute force method, that generates an optimal tour, but becomes essentially useless with even a moderate number of cities. And we have two other methods, the nearest neighbor algorithm and the cheapest link method, sometimes called the greedy algorithm, which we can compute readily enough, but they don't yield optimal answers. Maybe we just haven't been clever enough. Maybe there's a method that incorporates both virtues. Well, one reason the traveling salesman problem has intrigued so many mathematicians is that no one has been able to find such a neat solution, one that's computationally efficient and gives the optimal answer. In fact, most mathematicians now believe there isn't such an algorithm. But that doesn't mean we haven't made any progress at all. Remember what's wrong with the brute force algorithm. As we increase the number of cities, the amount of time it takes to solve the problem escalates very quickly. We call such an algorithm computationally inefficient. On the other hand, the time it takes to choose the nearest neighbor or to apply the greedy algorithm only goes up moderately as we increase the number of cities. Even with a lot of choices, you or your computer can readily identify the shortest links. What we do then is to give up our hope for optimal answers and to settle for methods that are computationally efficient and reasonably close to optimal. In most instances, for problems up to about 100 cities, methods have actually been found that do the job. Since the heyday of the well-traveled salesman, a lot of long-distance business transactions have been completed over the telephone instead of over lunch. And although there are now a number of long-distance carriers, there's still no better place to see how the national telephone service works than here at AT&T Communications in Bedminster, New Jersey. Rich Wetmore is the district manager of the Network Operations Center. Here, the day shift is often busiest because that's when most business calls are made. I asked Mr. Wetmore to explain what goes on here.
When a customer makes a call on AT&T's network, of course, what you want the call to do is go through. And what we try to monitor from this point in the country is the entire AT&T network, and we look for cases where a customer's call is not going through. We do that with our wall board, and the wall board displays data that's collected from all over the country and all over AT&T's network. And the wall board tells us when customers are making calls and they're not going through because there isn't enough capacity in our network. What we do when we see that type of problem is we change the way routing in the network works. We take normal routing and reconfigure it to route those calls via some third city, someplace else in the country that has capacity to the destination the caller is trying to reach. And when we put that reroute in, everybody's calls do go through and all the customers are happy.
Now, as you might imagine, there tends to be more long-distance traffic between New York and Los Angeles than between Nashville and Nogales. Does that mean that AT&T has to put in many more lines from New York to LA?
It's very similar, in fact, to the way you'd engineer a highway system for the country. Is between major cities, you have major highways and they have 10 or 11 or 12 lanes sometimes. That's the way our network looks. To smaller cities, you have 2-lane highways. That's the way the network looks too in terms of the circuits and capacity we provide. However, our fundamental principle is no matter where you live in the country, you should get an equitable type treatment in terms of the way the network performs and the blocking level you get. The traditional guideline we've always used, no matter if you live in Chicago or where I'm from, Horseheads, New York, is that you should get basically 0 blocking on the average throughout the day.
Since our constant goal is to strive for efficiency and economy, we want to construct a telecommunications network among some cities at the lowest possible cost. Every pair of cities has to be connected, but since it's okay to relay a call, the connection can be direct or indirect. If 2 cities are linked via a third, we'll consider that an indirect connection. We don't want to establish an additional direct line, which would just raise the cost of the network unnecessarily. We could approach this problem by applying brute force, the way we did for the traveling salesman problem. But if we tried to draw all of the possible networks and compare the total cost of each, it would take forever to compute. Maybe the greedy approach will work better. Let's start with the cheapest link. First, we make the 93-mile connection between New York and Philadelphia. The next cheapest link is New York-Boston. The third is New York-Washington. Now, the next cheapest link would be Boston to Washington, but that creates a circuit. So we don't need this direct link because we relay the calls the long way instead. so our algorithm would put in the next cheapest link that doesn't form any circuit with the links already established. As we fill in the rest of the necessary links, what we're doing is creating a special kind of graph called a tree. A tree is a connected graph that has no circuit. The cheapest communications network in a case like this is called a minimum cost spanning tree. The algorithm for the minimum spanning tree problem we described was discovered by Joseph Kruskal of Bell Laboratories. Although it's of enormous use to telephone companies, Kruskal was working on a pure mathematics version of the spanning tree problem. What's especially interesting here is that Kruskal proved that his greedy algorithm, which is quick and easy to apply, also provides an optimal answer for this class of problem. Unlike the greedy algorithm for the traveling salesman, what we have here is an algorithm that is both optimal and computationally efficient. This is a good moment to recognize that we've come upon some pretty profound ideas here. First, a number of management science problems lend themselves to graphical interpretation. Second, algorithms, or fully specified procedures, have been found to solve these problems. But sometimes there's a conflict between an optimal solution and a computationally efficient one. And third, some of the most useful practical solutions to these problems come from pure, not applied research. Joseph Kruskal's area was pure research, but Shen Lin, another top Bell Laboratories mathematician, has extended the importance of minimum cost networks to encompass very practical applications. His design for a computer software system has revolutionized the way AT&T's sales teams develop private telephone networks for their large business customers.
We do optimum designs better, I think, than most other people. And for a large corporation, for them to commit themselves to buy AT&T facilities and services, we in turn help them by reducing their costs, by giving them the most optimum configuration. So in a way, it benefits both the customer and also benefits AT&T. Of course, there has to be a mutual trust and some commitment in there so that a customer will not take the optimum design and replace the facilities out by other common carriers. But in general, we find that the customers have been very good when they get their designs done. They usually can reduce their cost by 5 to 10%, which in a network which costs maybe $20 million a year, that can be several $1 million.
If you prefer traveling to telephoning, though, don't give up hope. It turns out that progress in one application of mathematics often lends help in another area. In this case, the minimum cost spanning tree algorithm turns out to be the first step in designing a procedure to get relatively short routes for the traveling salesman problem. The method based on the minimum cost spanning tree algorithm is computationally efficient, and it's the only known method guaranteed to produce a route that's no worse than 1.5 times as costly as the optimal one. In many cases, that's good enough. This kind of result, proving that a method yields a solution no worse than a certain limit, is something we'll see again. Although it seems like many of these algorithms leave us hanging in midair, actually it's not a bad place for us to be, because airplanes are a handy way to think about a different yet related kind of problem. In case you're tired out from so much traveling, you'll be glad to know that for this problem, we're not going anywhere. The question here is not how to get somewhere in the shortest possible amount of time, but rather how to finish a sequence of tasks in the shortest possible time. Eastern's Bill Rottenheiser explains.
A typical aircraft turn is accomplished in 45 to 60 minutes. Basically what happens, the aircraft arrives, it is secured, passengers are offloaded. That process will take anywhere from 15 to 30 minutes. As soon as the last passenger off, the cleaners will be on board to clean the aircraft and ready it for its southbound departure. The caterers will have catered it, and maintenance will have checked the logbook and secured any items that be needed for a maintenance While this is being done, outside the ramp servicemen will be unloading the cargo, the mail, freight, and bags, and the fueler will be fueling the aircraft for its southbound trip. This will be adjusted during the off weather or bad weather days or heavy air traffic delays and whatnot, but we're all working under a time frame.
Let's simplify things by assuming that there are only 5 things that we have to do before a plane is ready to depart. Unload the old passengers, unload the old cargo, clean the cabin, load the new cargo, and load the new passengers. Now, we know how long each step takes, and we know that certain things have to be done first. We can't, for example, load the new passengers till the old passengers have gotten off and the cabin's been cleaned. And we'll also say that we can't load the new cargo till the old cargo's removed. There's one additional constraint. We can't load the new passengers until the old cargo's taken out. Now, that might seem artificial, but I want to illustrate the way in which mathematical models can incorporate the fine points of any particular situation. Anyway, it's not so very artificial. It could be that unloading cargo is dangerous, so that this is a safety requirement, or that the airline unions have insisted on it. This graph shows the 5 tasks with the time each one takes. We start at the left, work through all of the tasks, and finish up at the right. The arrows show where one task has to be finished before another can begin. This way of ordering tasks is called forming precedence relationships. One more thing. Our constraints will be defined by our need to maintain these precedence relationships and the deadline for completing all the tasks on time. This kind of model, where the edges have directions, is called a digraph. The shortest path in the graph is B through D. That only takes 47 minutes to complete, which is the sum of B and D's task times. But in order to do the whole job, we also have to accomplish tasks A, C, and E. Paradoxical as it may seem, if we want to find the shortest completion time for this network, what we have to do is find the longest path. What we're concerned with here is not the fastest time through the graph, it's the fastest time by which all the tasks can be completed. Instead of looking for the minimum time path, we go for the maximum time path. That leads us to this path for this particular problem, which tells us that it takes 55 minutes to complete all these tasks. That means the airline folks aren't leaving themselves much of a margin when they plan to turn an airplane around in 1 hour, something people who fly often have occasion to notice. The route we traced on the graph is what's called the critical path for this problem, and the technique we used is called the critical path method. What I mean by critical path is this: the sequence which determines the earliest finish time for the whole project. One of the most important applications of the critical path method is constructing a building. There are thousands of tasks involved in building, from drawing the architectural plans to ordering the parts and supplies, laying the foundations, erecting the walls, and finishing the interior. Some of these things can go on in parallel, but some can't. You wouldn't want to see the walls go up before the foundation's been finished. So contractors rely on the critical path method for determining a construction schedule, and architects use it to tell their clients just how long creating the building should take. There's another interesting aspect of critical paths that can save you a lot of money. Let's go back to our airport example for a minute. Suppose you were thinking of speeding up passenger unloading by building a second jetway. Those jetways are expensive, but maybe you figure that in the end you'll save money by turning the planes around a few minutes faster. So we can look at the effect on our graph if we reduce the passenger unloading time from 13 minutes to 7 minutes. Well, lucky for you and for your company that you know about the critical path method. As the new graph shows, there's a new longest path. That is, a new critical path that still adds up to 52 minutes. So even though you reduced the time of one task by 6 minutes, you only saved 3 minutes overall. Such a small gain may not be worth the cost of the second jetway. American Airlines Director of Operations Thomas Cook sums up the importance of finding cost-saving solutions to the airline industry's scheduling problems.
An optimal solution is defined as the best solution. So if you're trying to minimize a cost function of some kind. For example, we may want to minimize the excess costs related to scheduling of crews, hotel costs, costs that are not associated with flight time. And so what we're trying to do is minimize that excess cost, subject to a number of different constraints, like time a pilot can fly and how much time, rest time you have to give them and so forth. So an optimal solution is either a minimum cost solution or it could be a maximizing solution. For example, we might want to maximize the profit associated with assigning aircraft to the schedule. So we assign large aircraft to high load segments and small aircraft to low load segments. So it just depends on what function you're trying to optimize to whether it's a minimum or maximum. At American, we're probably one of the largest users of applied mathematics.
This critical path concept helps to dramatize two of the points that we've seen repeatedly in a variety of management science problems. One is that mathematical analysis can lead us to unexpected results. For example, that the earliest completion time comes from the longest path. And second, using models and graphs helps us to spot hidden relationships. Many problems which seem different, even opposite on the surface, can be solved with techniques that are quite closely related.